All right, so just like center of mass was not just, was about the mass distribution. Okay, rotational inertia is not just about how much mass something had. So the two girls had the same amount of total mass, but the juice boxes were distributed differently. So it's not just about the mass, it's about the mass distribution. Okay, so this is, pencil means please write it down. The rotational inertia, so I stands for inertia, capital I. And this is my notation or word blobs, meaning point particles, which hopefully will make sense by the end of this play posit. But it is the sum of every single mass, which is a blob. So think of it like your chemistry models, right? Those little white and red things that you make chemistry models with, those are your blobs. And each of those masses, so this is just straight out mass in kilogram, doesn't have direction, is a distance r away from the pivot. So the pivot being the girl's hand in the video. And there were two juice boxes, so you would calculate the rotational inertia of the juice boxes by taking the mass of each juice box times how far it was away from the girl's hand that was making it rotate, okay? And neglecting the mass of the PVC pipe that it was taped to, okay? So sometimes if you're taking this in college or on the AP, sometimes they'll use the word moment of inertia, which is like dipole moment. It's not about how much charge you have, but how that's distributed. It's not really an average because you're not dividing by mass. But it's some measure of where the mass is. Okay, so in general, I'm going to try not to use the word moment of inertia because it doesn't mean anything to you all now. I think rotational inertia is a better explanation of what it is, but just in case you're doing additional problems somewhere else. Okay, but it should make sense. I love the juice box video. The more those juice boxes weigh and the farther they are from the pivot, the harder it's going to be to rotate, the greater the rotational inertia. All right, so this is the new formula. Okay, what does it measure? Resistance to changes in motion, just like regular inertia measured resistance to linear motion. So the more the rotational inertia, the harder it's going to be to start spinning, but also the harder it's going to be to stop spinning. So like a pottery wheel, you might want to have a lot of rotational inertia so it'll keep spinning. All right, now we're going to do some logic questions. Which of these two objects has a greater rotational inertia? All right, it was a trick question. It is, oh geez, the animation doesn't work in Cami. It is a tie, because if you look at this, what they've done from A to B was let's just say they rotated this so that this mass was moved here and this mass was moved there. Okay, that's how you get from A to B. Did I move, in order to move this mass, did it move farther away from the pivot? Oh, sorry. This is like a bird's eye view of the batons that you're going to rotate. Okay. So moving this mass from here to here did not move the mass farther away from the pivot or closer to the pivot. So it did not change the rotational inertia of the object. So again, I pretend like somebody's holding this here and they're rotating it back and forth like the girls in the video were doing. All right, second question, which has a greater rotational inertia? I think you're going to have to calculate this one to get the answer. No, you won't have to, but I think you should know from logic, but do calculate it for practice with the formula. All right, without doing the math, you can see that between C and D, you took this mass M, and this is assuming that this point right here is your pivot. You took this mass M and moved it farther. It was down here. You moved it farther away from the pivot over here. So this should have a greater rotational inertia. And to practice using the formula, this is how you calculate it. You take every blob. So again, imagine these like blobs of clay on the end of toothpicks or something that you are rotating from a bird's eye view. So we have 1m, that's 2r away. You're going to square that, both the 2 and the r. In terms of space, I just lump these all together as 3 objects that are r away. And then this rotational inertia is 7mr squared. Then you do the same thing for object D. You've got 2m, that is 2r away from your pivot. And you've got another 2m that's only r away, and do the math, and you get 10. So this has a greater rotational inertia. All right, this is a little bit of a logic question, and then we will reveal the answer. Which object has a greater rotational inertia? Object A is a solid sphere of radius r and mass m, so like a super ball. Object B is a thin-walled hollow sphere of radius r and mass m. So pretend like B is like a basketball or a ping pong ball, but they have to have the same mass. So clearly, if this were a super ball and this were a ping pong ball, it would be more dense. You know, the wall would be really thick. Okay, so we can't change the variable m because clearly that would just bring more inertia. We're just changing the mass distribution. So which has a greater rotational inertia? So the answer is B, because if you imagine cutting that open, you have pushed the mass that was evenly distributed everywhere inside object A, and you've pushed it as far as you can to the outer edges while still maintaining a sphere. Okay, so B has a greater rotational inertia. And you don't need to memorize any of these values, even if you're taking the AP. Most of the time they give it to you. There's a couple you will need to memorize, but I'll go over that at the end. So the rotational inertia of the solid sphere is 2/5 mr squared, and of the ping pong ball mass distribution is 2/3 mr squared. These are clearly not blobs. This is what the mass is distributed in all kinds of different locations, if that makes sense. So like this little bit of mass is this far away from the pivot. Oops, sorry. This little bit of mass is this far away from the pivot. This little bit of mass is that far away from the pivot. You have to use integral calculus to derive these formulas. It is super cool. I'm not going to teach it. I will make a play posit for people taking the AP. They didn't used to emphasize it on the AP. They would always say, show that this is true, and you could always get enough points by just grabbing that value and doing the rest of the problem. But if you want to know how to derive some of those, I will do that for you. All right, those are the answers. Okay. Which object has a greater rotational inertia? Again, and they're showing you the blue line is the axis, so it's kind of rotating back and forth, or around and around like a record player, or like a tire spinning if the axle of the car were that blue axis. Okay, so we have a hula hoop that you're rotating around your waist. You have a roll of toilet paper. We're going to do a toilet paper lab in another unit. And you have like a dowel or a marshmallow. So rank these, or let's just say who has the greatest rotational inertia. Okay, and again, these are the equations for I tend to call this a ring. Sometimes it's called a hoop. This should make sense that it is mr squared, because all of the mass, if this truly has no width, all of the mass, every little single bit of mass, no matter where you look at it, is r away from the pivot. And that's the definition of rotational inertia. This is kind of cool. It's kind of hard to read, but this is all of the mass times the quantity, inner radius squared plus outer radius squared over 2. So this is I and O for inner and outer. So that's how we will calculate the rotational inertia of the toilet paper when we do that lab. And then the solid cylinder or disc has even less rotational inertia because you're bringing the mass closer, all the mass that was on the edge, some of it has moved in and filled in all of this empty space. And so it is half the rotational inertia of that. And deriving this is quite easy using calculus. But again, I will give that to you on the test. Okay, next logic question. Which object has the greater rotational inertia? Let's say you take a marshmallow and you squish it. Sorry, you take this marshmallow and you squish it, but it doesn't squish out. You just make it more dense. So which has a greater rotational inertia? And it is a trick question. It is a tie because I've squished this down, but I haven't brought any mass closer to the pivot or farther away from the pivot. Your reference is this pivot line. Okay, and that is what's, I think, a little bit hard, not a little bit hard, medium to tricky hard about, we keep changing perspective, right? Of like, what is the definition of distance? Depending, we're talking about work or we're talking about location. And the definition of the distance that we care about is how far is each mass from this axis. And so that this axis is our reference. We're just taking a straight line path to the axis, and that's what the distance is. All right, we're almost done with the guesses, but these are all important. Okay, so which object has a greater rotational inertia? Imagine taking a meter stick and rotating it about the middle or grabbing it at the end. All right, so center of mass for the meter stick about the middle is ml squared over 12. And it should make sense that B is going to be more because you're literally taking that mass. You can think of this mass as being the same as that mass. And you've taken this side of the meter stick and you've put it over here, which is farther away from the axis. So B is clearly greater than A. A third is bigger than a 12th. Okay, big fat warning. If somebody comes up to you on the street and says, hey, what is the rotational inertia of this object that I have, this meter stick? You can't answer that question. It depends on where you choose to grab it and rotate it. So remind me, I'll pass out hammers in class. If you hammer it the right way, it will feel very different from if you hold the business end of the hammer and try to rotate it. So you cannot say what the rotational inertia of an object is without saying where you're going to hold it and rotate it. All right, what do you think? For any object, a pivot passing through blank will always be the axis, which has the minimum rotational inertia. All right, I'm going to say this real quick and then you can pause this. If you are taking the AP, these are the three that they sometimes don't give you. Sometimes they do and sometimes they don't. They've been incredibly inconsistent. So I would recommend that you memorize it. MR squared is a ring. That should make sense. That's a definition of rotational inertia. The disk is half of that. That should make sense. You're bringing mass in. Be careful. This is the rod about the end, not about the middle. So I would just memorize these three and think of it this way. MR squared divided by 1, MR squared divided by 2, MR squared divided by 3. So it's 1, 2, 3 in terms of memorizing. All right, this is the last concept, and then I'll do the example problem in a different video. Plug and chug formula for calculating the kinetic energy. Just like linear kinetic energy was 1/2 mv squared, rotational kinetic energy is 1/2 I omega squared, because so linear inertia becomes rotational inertia and linear velocity becomes rotational velocity. It ends up being joules. Okay, that's kind of why I'm already going on 15 minutes. I'm not going to talk about that more, but it will work out. And then in the next play posit, super important. I will show you why this makes sense. Okay, so the two new formulas are definition of I, make sure that's in your notes, and formula for kinetic energy of an object that is rotating. Thank you for listening.